Yes, much better. So the Indianapolis experiment, I'm going to show you some data that we collected. So this is a lot focused on the tower network. There will be talks later on the aircraft mass balance and other parts of the entire deployment. So there are a lot of people listed here with a lot of contributions. You've seen some on the LiDAR already. I'm going to show you more the greenhouse gas part of the deployment. So this is the idea quickly, and you know that, but I think the real challenge of influx is to be able to map and identify temporal and spatial gradients. So we really want to go down to a level where we can go back to Kevin and just say this area doesn't fit our observations. We want to identify problems in space and time. So it's quite a challenging thing because you need to go down to the limit of the modeling tools that we are using these days. And we also would like to define uncertainties. And this is a critical question. I mean, Eric was talking about this. At this level, we don't know the truth, and we'd like to know. So we have to find ways to identify real signals from model errors, from data problems. So there are a lot of methods that we're trying to apply the same place on the same days. Most of the time we try. So there is aircraft flying around by the Purdue group. There is aircraft on automobile plume modeling. So it's more as a source at the point source level. And this is more related to methane emissions in this case. There is an inventory that has been developed by Kevin Gurney's group, which is a very high resolution product, sector by sector attribution, updated for several years. So we can compare also, we have interannual variability, seasonal changes over the city. And Indianapolis is maybe kind of a boring city compared to emerging countries, but it's actually changing pretty quickly. The Midwest has a very large growth these days, about 10 to 15% increase in the last 10 years in these big cities. So these areas are changing quickly as well. And then we have trace gases, so we have all kinds of fancy gases measured in the flasks, collected every week for now 2.5 years, 3. And then the mesoscale atmospheric inversion system that I will present in the same talk. So this is the network. Pretty much, we have all these towers downtown here, so all this network for CO2, CO, methane. We have these outside the city, so an upwind side, if you consider that the wind most of the time comes here from the southwest. We have some also remote sites that we hope could be a good combination of distant, total aggregated urban signals, but also maybe an upwind condition. We have very remote sites because the suburbs are growing. We'd like to also try to identify these patterns over time and space. We also have the TCON was deployed for 3 months. We have the LiDAR running, as Mike Hardesty showed earlier. And we have flux energy sites, so these surface energy balance sites. We have one in this forested agricultural area, one right downtown in a very heavy populated area, 2 which is on the suburb part of the town with a lot of commercial and traffic, and a nice site here which is a mixed green suburbs, so to quantify all the different types of landscape we have across Indianapolis. So now if you look at the data and you just do a very rough plot of all the data together, that's how it looks. Lots of noise, so noise of variability, synoptic, seasonal for sure. You can see the nice biological seasonal cycle, and this is not what we're interested in, right? This is actually the biology of both continental scale, regional. We're surrounded by corn. I mean, Indianapolis is in the Corn Belt. It's the eastern part of it. So you need somehow to smooth that in some ways. So you can take these afternoon values, actually, no, daily afternoon. It's still hard. You see a lot of synoptic variability, and you can zoom in. And now you start to see the gradients. So now you start to see that site 3, that was right downtown, being systematically higher than your site 1, that we can consider here as a background. Well, when we say background, and I will come back to that, how good of a background this is, because you really need to be constraining this as a box, like Kevin was showing this plot, and I will show it again. It's really a box model problem. What comes in and what comes out, and you want to know the difference. But you need to make sure you're measuring what comes in, and not a mixture of what is in and what comes in. So this is a challenge I will show. And then we still see large synoptic cycle events. So all the sites have this nice tendency. You can see still all this magnitude you'd like to remove, actually, from the network. So this is how it looks now if you consider that site 1 is your reference site. So you say site 1 is my 0, and now things are calibrated on site 1. You can see the enhancement for each site. So you start to see spatial gradients, site 3 being the largest one. Site 9, you see that you have a residue from the city, and then different part of the city and I don't show here the sectoral attribution, but you can see that some sites are more traffic influenced, residential influenced. So you start to see a lot of information spatially. And now you run your atmospheric model using Hestia, and you can try to see if you catch the same gradient. And yes, actually, you do a pretty decent job. You see that most of this enhancement in the model are pretty well captured, except like, oh, suddenly we saw a large difference at site 3. Systematic underestimation, maybe, for most of the sites we're always under. So we're going back to Kevin and see what could explain that. There are results coming, we have to dig more into it, but we start to find actually potential explanations for these discrepancies at the site-by-site level. This is not the inversion part, it's only the forward mode. So you already capture a lot of information just by looking at these spatially, without even running an inverse system. And so now the definition of the background. I mean, this is kind of, at the beginning, an easy thing. You just say, well, we measure upwind, we measure downwind, we make a difference, and here we go. Well, actually, not every day your site 1 will be a good background. So this is the fraction, the accumulative fraction. So how often your site 1 is really a background, or the lowest part of your network. And this is the enhancement. So, I mean, 40% of the time, yes, site 1 will be a very low, it will be the lowest site. But then also, I mean, sometimes you will see signals at site 1 because the wind is shifting. Sometimes you have a traffic signal, sometimes, so you need to consider that. And you can say site 1 is one solution. I can look at other sites. When a good candidate is site 9, it's actually a site very far away from the city. It's actually, yes, it's actually your second case. If you select when the wind is from the southwest, it's actually not at a good job because it's downwind of the city, but now it's in the southeast, you actually can use it. It becomes a pretty good site for the background. So we started to build this wind model that will pick the background site depending on the wind direction. So you can make this kind of more sophisticated box approach where you have a star network, and you can pick actually the best sites for the different periods. So once again, these blue boxes are really nice, so I want to show them again. This is actually the system. You measure upwind, you measure downwind, and you assume that in the middle with sources and sinks that interacted with whatever you measured. So you can use a fancy model. Let's say you go down to 1 kilometer in this case. We define our boundary in the initial conditions, both greenhouse gas and meteorology, to drive the model. We have prior flux estimates, so Hestia, we have a simple biological model, biogenic model, and then we have another inventory, which is more a global scale coarse product. And we have our 12 sites measuring CO2, methane, CO, and also fossil fuel data. So today I will focus on CO2. Now this is the fancy atmospheric system with, okay. So this goes from 9.3 to 1 kilometer nesting mode. So we zoom in the area. We have developed an FDDA system, so it's like a nudging system. You pretty much take all this, these are all surface stations. So we have literally hundreds in the area, and we force WRF to follow these. You cannot force absolutely WRF to follow everything, but you can force the model to agree as much as you can with the main wind direction, vertical profiles, and I mean, force the physics to go with the data. In terms of vertical information now, profiles, we are very limited. We have 1, 2, 3, 4, 5. Indianapolis is right there in the middle of the state of Indiana. So we don't have much information there, which is why we wanted to deploy this LiDAR instrument that becomes critical. We usually don't have the vertical information where we want it to be. The network is nice, but it has been made for large-scale forecast, not for urban-scale inversions. So now you run this system without the nudging or with the nudging, and you take some wind measurement at the surface, and you assess the errors. And so this is actually from minus, it's hard to see, I can help maybe, 80 degrees, yes, sorry, 80 degrees in the wind direction, and you can see with and without, so absolute error in red and the mean error in blue. Now with FDDA, you can see how you can decrease your errors on an hourly basis. So that helps you a lot by getting the mean wind direction, and you really need to know where the wind comes from. A small bias error systematically on your plume may be dramatic in terms of how you extract the information from it. So yes, the FDDA improvement is nice, and on top of that, we can have hourly information on how the model performed. So I can actually tag each hour in my inversion system and say this is reliable information or this is not good information. So we kind of improve the way to evaluate transport errors in our inverse system by also having these meteorological data in it. So that's quickly an inversion result. I used here, so this is a five-day emissions. It's not a typical way of looking at emissions, but I want to show here the cycle we got from September 2012 to December 2012. If I start with this dashed line, which is Hestia 2012, and I run the inversion using this wind model and all these system, this is my the line here, and we agree actually pretty amazingly well. So on this test period, we got a very good agreement with the Hestia product. I tried to do the same thing with using ODIAC, which is really this nighttime satellite product where you map emissions in kind of a very bold way. You just say, this is my total emissions, here is where people live, this is where emissions are. So it's really a bold way of looking at this problem. And you start with this kind of dumb flat prior, and you actually start to include information in it. So that's really going into the direction where we don't have a good prior, because in many of these cities worldwide, we do not have good information on the emissions. So we may be starting with this ODIAC product, for example. So that's the potential of only with atmospheric information and a global scale product, what we can actually retrieve. This big discrepancy here, actually, looking back at fossil fuel data, is because I'm too early. It's still the growing season, and we still have biological signals. So actually, the sink has been converted into a source to compensate for the mismatch. And now you can look at spatially, and in this case, we actually found out that a lot of the discrepancy was on the rings. This is the beltway around Indianapolis, and this is a percentage change compared to Hestia. So after inversion, before inversion. Talking to Kevin, we may have an explanation. I'm not going too far in that, but it seems like on the road traffic emissions, we may have found something that is really consistent with what the inversion identified here. So we see clearly signals. It's pretty amazing to see that the ring has been really identified by the network. We'll see now if it's really a true signal or if it's just some other problem in the system. And now you can do all kinds of tests, because that's really where we're going now. How good is the system? So you can play with different prior emissions. You can play with the number of sites you're using. You can also play with the correlation, because when you build that thing, you made a lot of assumptions. You just say, are all the traffic emissions the same? Should I change the city as a whole or by pixel? So you have a lot of underlying assumptions that we don't discuss much, and we don't have much information to actually guarantee that these are reasonable assumptions. So we're trying to test that. Different configurations, because we may not have 12 sites everywhere in each city in the world. So how many sites we really need, and what can we achieve with a limited number of sites? Can we get the spatial information, the temporal, on only the whole city emissions? I have the wind model. Is it really useful to have this hourly information on the transport errors? And then you can use different assumptions on the way to define your background. Is my background the daily value over the minimum of my period? Is it my fancy wind model? Is it an hourly value that keeps changing? So you can make all kinds of reasonable assumptions and see what could be a good one for this whole city emission problem. So I won't go into details, but you can see that the numbers vary. They do vary quite a lot. I mean, you can see that this is not, you start with different numbers, but you don't end up with exactly the same numbers. So these are all assumptions that we need to work on and identify better ways of evaluating the best way to approach these. So this is the first time when we look at all this amazing amount of information in the data. I mean, it's pretty impressive to see that even two sites 10 kilometers away show you totally different responses to these signals. These are very strong signals, but also very local. These are point sources. So you may have a power plant in the middle of Indianapolis, and then you have a highway next to it, and then you have these commercial areas, and all have very different cycles. So it's a lot of data we have to collect and information to extract from that. The data, so we are using also this problem of the background, and trying to develop this data assimilation system to actually extract all this valuable information that is pretty high level. So I'm going to stop there because it's blinking. Thank you.
We'll take one quick question. John?
Question about the background. I was wondering if you have done a test of using some global CO2 output as the background. So that might be the case for a lot of cities where we don't have a background.
You did it. You want to answer? Okay, so Jocelyn tried, and actually she showed in the article using the fossil fuel that it's pretty bad background, and we cannot do that. You use LEF, right? Tower, or yes, at LEF tower, and it was actually it created a bias and artificially increased the emissions, compensating for signals at LEF.
How about carbon factor or
Oh, we haven't So my experience, my trauma from the MCI is that carbon tracker can be really off on an hourly or daily basis. And so I didn't even try.